as much as I love PowerPoint, I'm going to have to forego it today since this is a last minute kind of call for me. So today I'm going to talk about what some of you are probably familiar with, and if I have time, a second thing. So as many of you are aware, I've been interested in this concept of combining expansion microscopy with X-ray microtomography for a while now. And I recently won one of the AI safety grants to pursue this technology, and I am working with a company called Panluminate to do this, as well as with collaborators who have access to synchrotron imaging facilities. Why am I doing this? Because the scaling of the imaging speed for going from mouse brain to human brain, which, as we've heard, mouse brain is already a pretty big challenge. Human brain is about 2,400 times the volume of the mouse brain, and isn't really feasible, in my opinion, with the existing technologies or even some of the really innovative new technologies that are being developed. And so my thinking is that we need a imaging modality that is a lot faster. And so what I'm looking at is this combination of expansion microscopy, making everything bigger to increase the resolution, and then because the expansion microscopy also increases the imaging time since there's a larger volume, taking advantage of synchrotrons, which are a type of particle accelerator that emits brilliant X-rays, to image human brain really, really fast. And in this case, it would mean about 1 year of continuous imaging, given the projections and the calculations that I've done. And obviously, that's a very speculative estimate, so that a lot could change between now and when that would hypothetically be done. But 1 year of continuous imaging to do the whole human connectome, and that's just the imaging part. That's what I'm aiming for. Right now, I'm starting off small. I'm starting off with the technology development because this is a very new approach. Nobody's actually combined expansion microscopy with X-ray microscopy before. And so I'm just doing small pieces of tissue in collaboration with Panluminate and with my EMBL Hamburg, where they have the synchrotron, and working on that stuff. In other news, there may be some interest here. I recently posted a preprint, which I wrote along with Randall, on comparative prospects for EM, electron microscopy, and expansion light sheet fluorescence microscopy. The X-ray stuff isn't really included in that because the X-ray stuff is maybe a little too speculative right now to be included there, but I think it gives a good, it's a preprint right now. I shared it in the Signal group. And I think gives a good overview of sort of the landscape of existing technologies and how long different imaging technologies would take to reconstruct whole brains. So with that, I think I'm going to shift gears if I have time, and I'm going to say I'm also writing a grant which is it's actually an NIH grant for a predoctoral to postdoctoral transition fund, which would essentially fund part of my predoc and all of my postdoc, essentially. And what I'm interested to hear is probably highly interesting to a lot of you. It's essentially a spatially targeted way of growing parts of the brain. So being able to point focused ultrasound at parts of the brain and cause it and cause those specific spatially localized parts of the brain to grow. For the NIH, I'm targeting this as a treatment for Alzheimer's. For you guys, it's probably a lot more interesting to think of this as a way of enhancing human intelligence. And obviously, there's there's more to it than that. But anyway, the idea is to use a blood-brain barrier crossing virus called adeno-associated virus, which certain serotypes of it that have been engineered to cross the blood-brain barrier, to distribute a gene throughout the brain that can be activated upon induction with a slight increase in temperature. And focused ultrasound is capable of having spatially localized increases in temperature. So you can imagine that if you injected this virus into the bloodstream, it goes to the brain, then you'd be able to regenerate or even enhance the growth of certain parts of the brain at desired locations. And if anybody knows somebody in Boston who works with Alzheimer's disease, I'm looking for a letter of support from such a person, because that is something that would be very helpful for the grant. And so with that, I will take questions.
Thank you. pretty slick without slides. Thank you so much.
Very interesting. And this is questions from the caused by the lack of the slides.
Sure.
So is there a proof of principle that expansion microscopy-based method used for connectomics?
So there's actually was a recent preprint where they used confocal fluorescence microscopy. They developed a technique Lycon, I think it's light microscopy connectomics or something like that. And they actually did show that they could do dense reconstruction of neurons in a small piece of tissue using light microscopy. Right now, they used a 16-fold expansion, and they the confocal method they used was probably a higher resolution than could be done with light sheet. But I think if they used a higher expansion factor, like 20 or 25-fold, which is possible now, they could probably do it with light sheet microscopy. And then with the X-ray stuff, it could definitely, I mean, the X-ray stuff is, again, more speculative even than the light sheet, but because right now I'm like really the only one of maybe two people who are pursuing this kind of thing. But the X-ray, it's definitely something that I hope to make possible so that we can take advantage of those synchrotron imaging speeds.
Thank you.
Yeah.
So I was curious on just in terms of how much, like what kind of thing the X-ray contrast shows you about the cell. Like you never heard about it. I was super curious, just reading about it last night. And like in terms of contrast, what kinds of things, what kinds of information you get? Do you get, if any, what kinds of molecular information? Could you like use these like unclearing stains to like stain for molecules? If so, for how many potentially current? Because if not, it'd be just a strict replacement for EM, but not for optical connectomics, right?
Right, so I would say that it's maybe partway in between EM and optical connectomics. I think that it will be possible to develop ways of doing several colors. I would be a little bit more hesitant to argue that we'll eventually get to the point where we can maintain the same speeds and do a lot of colors. So the reason I say several colors is because you can use absorption-based methods to do multicolor X-ray microscopy with 2, maybe 3 colors. The unclearing methods, as you mentioned, you might be able to tag with different materials that would give different phase contrast. I actually am not sure at this point how differentiable different types of phase contrast would be in an X-ray microscope, but it's definitely something that's worth exploring. So I should make a distinction here. Right now I'm pursuing phase contrast X-ray microscopy as opposed to absorption-based because it drastically lowers the X-ray dose that's needed and means that there's less likely going to be damage to the sample. But yeah, I think that there are definitely some possibilities for multicolor. However, having like 30 colors or something might be very challenging unless the technology behind X-ray fluorescence microscopy really catches up to X-ray phase contrast and X-ray absorption stuff.
Thank you so much, Logan.
Thanks.
Okay.